Lab 3 is about black holes. Okay, so we wanted to calculate the mass of the black hole that's given to us and also calculate the initial velocity that it needs for a spaceship to take off under the force of gravity. So we needed to construct two different computational models, one representing the trajectory of a star around the black hole and the trajectory of a spaceship around the black hole that takes off from the planet. So the main two formulas that we're going to use are the momentum principle, where we have momentum is equal to mass times velocity, as well as writing that the change in momentum is equal to the mass times the change in velocity. And we also use Newton's second law to derive that formula from the net force is equal to the mass times the change in velocity over the change in time. And these two formulas are important because they're going to help us calculate some things that we need to know about both the star and the spaceship. We use the velocity and position update formulas from Newton's second law, finding the net force, and the momentum principle to help us find the change in momentum. Now, for the first part, we set the initial conditions. We define the gravitational constant, the star mass, and the delta, and the change in time. Now, we converted that to seconds so that we can keep the velocity in terms of meters per second. But after running the GlowScript code for a few times, we found that the mass of the black hole actually fluctuates as the star revolves around it. So you take the average of it, and it's estimated to equal about 1.3 10 to 34 kilograms. And we calculate the mass of the black hole by deriving from the formula for finding the universal gravitational force on an object, where we take the gravitational constant times the mass of the source times the mass on the system divided by the magnitude position times r hat. As you can see, defining lines 192 through 194. And then we begin to identify the momentum of the star. So starting at line 163, we identify the initial and final momentum vectors using P equals m times v for both the initial momentum and final momentum. We calculate the change in velocity by taking v final minus v initial and the change in momentum by using the formula that we discussed of the change in momentum is equivalent to the mass times the change in velocity at 168. And then we need to calculate dp dt, which is already from Newton's second law, we know that it is equivalent to the net force. And then it asks us to find the parallel components of the net force, in which we need to use the dp dt, where we take the magnitude of the momentum times the change in time times p hat. And so once we find f net parallel, we can set it equal to, we can also find the perpendicular component by taking the net force minus f net parallel, since the sum of the net force is equivalent to the sum of its parallel and perpendicular components. And then when we move to part 2 is where we want to begin to find the initial velocity of the spaceship. So we set our initial conditions, the mass that we found in part 1, the gravitational constants, the change in time. We want to set the planet speed and planet velocity. We don't want to touch those, but we also need to find what the ship speed X and Y components need to be so that it doesn't crash into the planet and can fly around the black hole. And for that, we found that its velocity is about -5 times 10 to the 7th in the X direction, 2 to the 10 to the 6th in the Y direction, 0 in the Z direction, meters per second. Now, the computational model that we need to do is this, that we need to find the net force on the planet by the black hole and the ship, and also the net force on the ship by the black hole and the planet. So what we did for that was that we again use the formula when we use the gravitational constant and put things and defined r at 79 and 83 and defined r hat at 80 and 84, so we could find the total force on the planet. And we did the same thing that we did for finding the net force on the planet as we did for finding the net force on the spaceship. And then after doing that twice, we had to make sure that we had the iteration of Newton's second law to determine the velocity and position update of the planet and the spaceship. So we needed to use v final equals v initial plus the net force divided by the mass times delta t, and position update formula where r final equals r initial plus final velocity times delta t. And so that's what you see in lines 111 through 116, where we're both updating the planet and ship's velocity and position. So by applying the momentum principle, which we can derive from Newton's second law, we can calculate an object's net force, its components, and we can understand an object's trajectory. And by estimating the mass of the black hole, could have also caused some sources of error when we calculated the net force acting on the planet and the ship, and therefore also the values of velocities of the planet ship, since Newton's second law uses the net force divided by the mass. Now, for our what if is when we want to change that, we decide that we want to orbit the black hole and not just take off the planet. The easiest way to do this is to just take the magnitude of the x component and to make sure that's less than the magnitude of the y component, so that it takes a trajectory similar to the one that you see on the right, where it's orbiting instead of taking off. And the values that worked for me best was when I used -2 e to the 6 for my x component and +1 e to the 7 for my y component. And then for the what does it mean section, ask us how does the net force and its parallel and perpendicular components compare to the parallel and perpendicular components of the change in momentum. And since Newton's second law states that net force on an object is equal to its rate of change in momentum, then we can declare that we can conclude that there is no difference between the perpendicular and parallel components unless they are equivalent.